Hey, geometry students. In this lesson, we are going to be talking about how to find the surface areas and volumes of prisms. And actually, we're also going to talk about pyramids too. That just doesn't quite make it to the title because it's not an important enough part of this lesson. Now, when I say surface area, there's a very specific thing that I mean by that. The same thing with volume. You're going to find that this lesson is really easy, it makes a lot of sense. There's one hard thing a little bit later. We talk about oblique prisms, but even those aren't that difficult to do the math on. They're a little more difficult to understand why they work the way that they do. But there's nothing difficult with the math of this lesson. So that should be very reassuring for you. Let's get started talking about surface areas and volumes of prisms. We're going to start by defining the surface area. This is the total area on the outside, all faces, all curved surfaces of a solid. Surface area means something very, very specific. It means that you're measuring the area of all sides, all faces and all curved surfaces of whatever figure it is that you're looking at. Lateral area. Now, just be aware that sometimes you're going to be asked to find the lateral area. Notice I didn't say lateral surface area because surface area specifically means all of the things. Lateral area is just the total area of the lateral faces. And when I say lateral faces, basically what I mean is we're excluding the bases of a pyramid or prism. Okay, now, you see the word pyramid there? That's how pyramid works its way into this lesson. We're really going to be specifically talking about prisms. But you could find, I just want to make sure you understand when I talk about lateral area, I could be referring to a pyramid. And the only thing that's not included in the lateral area is the base of a pyramid. For a prism, it's both bases get excluded from the lateral area. So it's just the area of what we would regularly call like the sides of the figure. All right. There's a very specific formula. It may surprise you just a little bit for the lateral area of a prism. You might think, oh, we have to find the area of a side and then the area of another side and add them together. For a prism, remember too, the sides are always either rectangles or we're going to find parallelograms are another option. Well, here's the thing. For a prism, the lateral area is found by finding the perimeter, P, and then multiplying the perimeter times the height. That makes it a lot easier because now we're not adding together different faces. We're just finding the perimeter of one of the bases and then multiplying times the height. That'll always give you the lateral area. The surface area, this one we have to actually add together all the faces. So what we need to do is find the lateral area first. Okay, you could find that by adding together the areas of each face, or you could find it by finding the perimeter of the base and multiplying times the height. But then we have to add to that the area of the bases. We have to 2 times the area of one of the bases because in a prism the bases have to be exactly the same. The volume of a prism is going to be the area of a base times the height. We're going to say specifically, though, height needs to really be replaced with the word altitude here. Okay, in a right prism, the altitude is the height. What do I mean by a right prism? A right prism, these are the ones we're used to seeing because most of the time when we've seen prisms pictured in the book, they've been right prisms. All of the lateral faces of a right prism are rectangles. And then all of the lateral edges, what this really means that the lateral faces are rectangles, all the lateral edges are perpendicular to the bases. This is an example of a right prism. Notice that all of the lateral faces of this are rectangles. And that's going to be true of all right prisms because that's the sides of a prism. The faces are always rectangles in a right prism. Now, and there is another type of prism known as an oblique prism. At least one of the faces is non-rectangular. That's this. Now, it takes a little bit to understand the perspective here, but notice that if I were to stand this on end, normally if this were a right prism, this triangular base would be at the bottom, this triangular base would be at the top, and everything would line up. But I've taken this base and basically just shifted it over to the side, and now everything's tilted to the left. So now at least one of my faces is not a rectangle. It's a parallelogram. Okay, notice that this face is a parallelogram. Therefore, this is an oblique prism and not a right prism. This brings up the concept of an altitude of a prism, because normally the altitude would just be the height for a right prism. Notice that because the bases all stand perfectly upright, I can just measure from the bottom base to the top base and I get a straight perpendicular segment. Well, when we're dealing with an oblique prism, notice that I have points on one of the bases that hang out and they aren't over the other base. So I can't just draw a line of a perpendicular line that's perpendicular to this base and this base that touches both bases in all cases. So what we end up defining the altitude of a prism as, and pay attention to this, it's a segment that's perpendicular to the planes of the bases. Okay, so this is perpendicular to both bases and has endpoints on the planes of both bases. Yeah, that's how we have to define an altitude, because we're not dealing with a figure that's standing straight up anymore. And then here's the great thing about the volume of a prism: the formula doesn't change. This H here, it only stands for height when we're dealing with a right prism. You could just plug in the altitude of an oblique prism and the same formula works. Okay. Um, hey, one way to think about that is, imagine we have a whole bunch of paper thin triangles, okay? And we're stacking one triangle on top of the other to make a triangular prism. If I stack them straight up, I'm going to have the same number of triangles if I stack them straight up for this height as I would if I stacked them just offset a little bit to make this oblique prism. So I don't know if that helps at all, but the formula for the volume of a right prism is going to be the same for the volume of an oblique prism, just so that we replace the height with the altitude when we're dealing with an oblique prism. All right, let's do some practice problems and see how this works out. We do have one oblique triangular prism here we're going to be finding. All right, let's do this. Letter A, find the lateral area of the prism. All right, well, this is going to be, we're going to do this. There's multiple ways to do this. We could just find the surface area of all four sides, or the area of each of the four faces, and add them together. A better way to do it, though, is what the book recommends. Let's find the perimeter, and then we're just going to multiply that times the height. So the perimeter is going to be 9 plus 7 plus 9 plus 7, or 2 times 9 plus 2 times 7. That's 18 plus 14, 32. Okay. Now I have a perimeter that's equal to 32. In this case, it's yards. I'm just going to put a P there. So remember, we're dealing with perimeter. And so we've got 32 yards. Now we're going to multiply that times the height, because the perimeter times the height is the lateral area, so it's going to be 32 times 15. I see I have a height of 15 there. I'm just going to punch it into a calculator to get it done quickly. 32 times 15 is 480. So it's going to be 480 yards squared. Dealing with area, so my unit's going to be a square unit. Let's just make sure we did that right. 480 yards squared. Find the surface area of the prism. Not just the lateral area, but the surface area. That includes the area of the two bases. So it's going to be 480 plus the area of the bases. Okay. So that's going to give me, let's see, for the bases, it's going to be 7 times 9. So 7 times 9. And then there's 2 of those. So it's going to be 2 times 7 times 9. Let's see, 7 times 9 is 63. 2 times 63 is 126. So this is going to be, and remember my formula is the length plus 2 times the area of the base. So this is 2 times the area of the base, 126 yards squared. To get the whole surface area, I need to add these two numbers together. Just looking at it, it's going to be 606. So we're going to say the area equals 606 square yards. And let's double check, make sure we did that all right. There we are. All right, on to letter C. And for this one, we need to know how to find the area of the base, right? Because we see that this base is a pentagon, and we're asked to find the volume. So we need to find the area of the base times the height. We have the height, we have 14 centimeters, one of the edges. This length is a very special length for a polygon known as an apothem. And by the way, if you ever see a dead apothem, don't get too close to it because the apothem might just be playing dead. You don't want to get rabies. Okay, anyway, what we need to do is let me just draw out what we're looking at here. And I'm going to grab a I'm going to grab a regular pentagon. And I'm just going to show you, we have this length called the apothem that goes toward the center of it. Now you can't unhear me lisping saying the word opossum, right? All right, so I'm going to do this. Let's see, and we'll connect this. And I'm not doing this perfectly. I'm just doing a sketch of this, okay? So this is not exactly right. Hey, if this is a triangle inside my pentagon, how many of these triangles do you see? If I would have drawn this perfectly, how many triangles are there? Well, there's 1, there's 2, right? There's 3, and here's where we're going to see how imperfect my drawing actually is. 3, 4, and then 5. And I'm going to take all of my apothems, I don't know. I'm going to take all of those apothems and I'm going to make them dotted lines so it makes it a little easier to count the triangles. So let's do this. Okay, so each of these dotted lines is an apothem of this pentagon. And then the solid lines represent the actual triangles that I'm drawing. How many triangles are there? There's 5 of them, right? And can we find the area of one of those triangles? Why, we sure can. So here's how this one's going to work. In letter C, we're going to have 5 triangles, each that has an area of 1/2 times the base, 14, times the height, which is the length of the apothem, 10. All right. So 5 times 4, 1/2 times 14 times 10. Well, 14 times 10 is 140. You multiply that times 5, and I believe you get 700. And then 1/2 of 700 is 350. We'll check in just a second to make sure I did my math right. That's going to be centimeters squared. And that's the area of the um, pentagon at the bottom. Now, I should be able to take that and multiply it times the height. Let's see if I can do that. This is going to be 350 times 22 using a calculator, 7,700. Let's see if we get this correct. First of all, I'm just going to note that my volume is 7,700 centimeters cubed. We're going to have a cube unit here, okay? And then let's just double check my answer. There we go. Now, I'm going to take and just move this guy down here off to a safer place. So we don't want our apothems getting hurt. All right, in letter D, we're finding the volume of this oblique prism. And then just once again, this is going to be the same formula we always use. We're not changing anything up. It's going to be the area of the base times the altitude. The area of the base of this prism is the area of that triangle. And I see I have an altitude there. Notice that it's perpendicular to the base of the triangle. So 1/2 times 3 times 5. Okay, and then multiply that area times the height, times 12. 1/2 times 12 is the easiest to multiply together. It's 6. 6 times 5 is 30. 30 times 3 is 90. This should give me a volume of 90 feet cubed. And let's just make sure we did that one right. 90 feet cubed confirmed.